can start. You can start.
Okay. Hi, Shruti.
Yeah, hi.
Okay. Like, tell me about your experience in PD, PD or PV.
No, actually, I don't have an experience.
Okay.
I have a gap from 2019.
Okay. Like your education qualification completed BTech.
MTech. 2019, I completed my MTech.
Okay.
Hmm.
Like, do you know about the LBS? Can I start with LBS? What is LBS?
What, IVS or
LBS.
LVS?
Well, you can answer with lyrics are the same questions. Fine.
Yes, sir.
Yeah, we can. Yeah, you can parallelly take his interview also. Like both the people have to.
Okay, sir. Yes, sir. LUS means layout versus schematic. It is an method to check whether the produced netlist in a PNR step and is used to compare with the original netlist that was generated after synthesis.
Okay, fine. Uh, I for one case I have it. You be like, do you know what are the tools do you work? What are the tools do you work for? Like Caliber, Innovus,
I have worked on
ICC.
Synopsys DC, ICC2, Star RC, and Prime Time.
So what are the most difficult LVS setups do you face? Like for both of the candidates, for Shruti and Vicky.
Yeah, in my designs, I haven't faced that much of LVS. I have did the timings and off using Prime Time.
Can you repeat it again for 1 second?
I have done till timings enough. I haven't gone for physical verification. I'm not having much experience in PV.
I will give you a case like, for example, you have a shot between macro M2 pin, and it is starting with like the signal M2. How do you find that shot?
That shot will be found out by using check LVS max error 0 after routing.
Okay.
So,
No. Like if it is M2 pin, internal M2 pin, we cannot do with check LVS. We have to run the full run LVS, like LVS dot sum. If it is short between power or signal to signal or power to ground, then we can check with check LVS. When it is short with internal pin, with the macro pin or internal pin, so that short we cannot be checked in check LVS.
okay.
We have to run the full run LVS, like LVS dot sum report. Whether the tools which are used, for example, in Caliber, use Caliber or ICC, like
I
in
used
our
ICC2.
okay, in like ICB or like you will run like in Caliber version or ICB version.
ICC.
Like in full run, we can check with internal shots. Okay.
Okay.
Like what are the steps do you follow in PD flow?
In PD flow, first floor plan, power plan, placement, CTS, routing, and sign off.
Okay. Like
That's
during the foreplan stage, like whether first you will do the physical insertion placement or like power grid stage.
physical insertion. First, we place the macros. Then
Okay. So I will give you a case like uh what are the cells what are the cells like will be placed in physical insertion stage?
in floor plan, we generally place macros.
Okay, after macros
After macros,
in
then
phys
we will place capsules.
okay. Do you have a read about bound work cells?
Yes, it's boundary cells, encapsulates.
No, bound buffer cells. Bound buffer
Boundary
cells.
cells.
BOUND,
No,
bound
I
buffer
haven't heard.
cells.
I haven't heard.
So, okay, those are the cells will be placed in like physical insertion cells, right? So the cells like from the cells used to place, for example, you have working on tile level. So from chip tile to tile level, if any connections is there from chip tile to tile level or from tile level to another tile level, those cells will also be placed in physical insertion cells.
Okay.
Okay. Do you have do you tell me about antenna?
Antenna is a ratio between metal to the gate area ratio, metal area to gate area ratio.
Okay.
Uh, it is
So if you, yeah, continue.
it is an after it is mainly occurred in while fabrication. I mean after etching, after plasma etching, uh, we might see this antenna effects.
So how do you like to get antenna effect, like antenna error? How do you like? What are the process to reduce the antenna?
To remove the antenna effects.
Yes, to remove the antenna.
We can use metal hopping. Uh, like if
Okay.
we routed the metal in the metal one till the gate, till the gate of the transistor, the MOSFET, we can hop that metal to the M3 or M4 higher layers, so that we can reduce the antenna effect. Or we can also use diodes to
Mm-hmm.
remove the antenna effects.
Like what diode do you use for to reduce the antenna?
Uh, a normal diode, PN junction.
Usually it will be the reverse bias diode, and
Yeah, sorry, reverse
uh,
biased. Sorry.
it's the reverse bias diode to reduce the
Yes,
antenna.
reverse biased.
Mhm. Okay. And uh, what are the like physical cells do you see in the block in your tile level, in the partition of the tile level block level?
Block level physical cells, decap cells, end cap cells, cap cells, um, and some other filler cells like say, some boundary cells. Yeah, that's it.
Do you have about space cells in the design and why they're used?
No, I haven't had any spare cells in my design.
Okay, okay, there will be space cells in the design. So those cells will be used for example, like uh, once the design is completed and you want to insert some cell for timing fixes. In those cases, we will remove the space cells and we will keep the timing cells for fixing them.
Okay.
Um, and do you know about latch up?
Yes, latch up. Latch up
Tell
means
me.
nothing but the formation of a transistor, I mean, a thyristor in an
Mhm.
PWL, a piece, envelope piece of shit. Due to
Mhm.
this, some shorts will be occurred in an example of CMOS. So to remove that, we will using capsules.
Okay. So for how many microns will place the capsules?
Sorry,
Like
sorry, I
on
can't
what
hear.
technology not you worked? Like on
14
what
nanometer.
what?
14
Like
nanometer.
for okay. For how many microns you use to the capsule?
30 microns.
30.
Yes, 30 microns in a checkerboard fashion.
Okay. Okay. Mm-hmm. What are the most difficult DRC error you face?
Most difficult DRC. So in my, I have worked on a large design around with 1 gigahertz frequency. In that, I had around 150 macros.
50 macros.
So
Okay.
150 macros. And in the
Okay.
channels, there were some shocks.
Mhm.
So I had to clear them. That was a little bit difficult for me.
Can you repeat again?
In the channels,
Okay.
there were some shorts
Okay.
between some standard cells and some logging. So due to that, I had to fix those shorts manually. It took me a little bit time,
Mhm.
but I have cleared most of the shorts in my design.
Okay. Like for cleaning the LVS, what are the steps do you follow?
First, after routing, I have checked for check IDs to click opens and shorts. And
Okay.
after getting
Do you
the
need check
shorts,
LVS?
yes, check
Do you?
LVS,
Oh, okay. Okay. Mm-mm.
max errors 0, hyphen max errors 0 is the
Oh,
command
okay.
I have
Okay.
given. So it gave
Okay.
me the list of opens and shorts.
Mm-mm.
And then in the GUI, I have
Mm-mm.
opened those shorts manually and checked which methods are having shorts, and then I cleared by removing and replacing with bias or a little bit manual fixing I have done with moving wire to a side to clear the short.
Okay. Okay. And for antenna, you got it. Like usually we will check the antenna, and after that we will do for metal layer hopping and prior insertion.
Right.
What are the cases do we take? Like what are the precautions do we take to like before doing this, before coming the antenna error? How can we take care of antenna in the design?
Before means we should use higher metal layers if possible.
Here,
So higher metal layers if possible
okay,
to have the more current density and usage of uh, HVT cells, not HVT, LVT cells. Have better. They also
okay.
have the leakage.
We can place the tie cells in the design. Uh, so tie cells and for like antenna will mainly occurs on like it won't be occurs on power nets and special nets and clock net cells. For the remaining cells, we can place the antenna cells there for the input and output, or we can add tie cells in the design. It's a like precaution without getting the antenna. So this is like one method, like precaution type. Mm-mm-mm. So what are the errors do you face when there is a hole in the design, like a gap in the design?
Uh, what gaps are I cannot understand properly.
Like uh, hole is like
Hold,
what do you call
yeah,
it?
hold check. Yeah, the
Yeah.
main issue was in the design I have mentioned earlier. I have seen some
Mm.
hold issues. So for
Okay.
that, I have placed buffers on the nets which were having the hold issues. The only way to reduce the hold violations.
Yeah. Do you ever work on always on VNO regions power? Always on power VNO power?
Um,
Yeah. Okay. Okay. Fine. Mm-mm. Okay. So, do you work in Caliber?
I have used mainly synopsis tools only.
Synopsis. Okay. Okay. Fine. Uh, like for example, in the boundary region, we have placed a tap cell. So, what are the errors you will find if there is a tap cell in the boundary region?
Uh, Mainly VLSI will be occurring because and boundaries only encapsulates should be present. Some DRC tab cells are placed instead of encapsulates like that. Some DRC will be present.
Okay. Okay. So all the base errors as for example, if we place a capsule near the boundary, we will see the PO errors, OD errors. Those errors we can see in the boundary, in that region, PO errors, OD errors, VT errors. There's different in the VT errors. Like those errors we can see near the error location.
Okay.
And do you know about EMIR, electromigration? Can you tell about electromigration?
Electromigration is mainly caused in a long time due to the high currents that are passing through the metal layers. So due to the high currents passing through the metal layers, the atoms in the metals gets redistributed so that they have shorts or opens can occur between the metal
Okay.
layers in the long run.
Okay. So what are the precautions, like how to reduce those, how to reduce EMIR?
So to reduce electromigration, we can use high metal layers if possible, and also we have to maintain some voltage regulation to control the
Mhm.
current and the voltage that are supplying to the MOSFET.
So I give you a case like, for example, on metal 2 layer, we are getting signal EM. So the violation, the margin is very less, and the
Okay.
length of the metal is also less.
Okay.
So how you will like reduce a margin for that metal until signal EM? Think, take your time. And
I'm sorry, I cannot recall it.
okay. So J is equal to I by WA. J is the current density. Like W and A is the width and area. So if we increase the width of the M2 layer,
Okay.
we can increase the density there in that region. So in this way we can. So for example, M2 having lower width and it's a small margin, right? So in that
Yes.
region, no need of robustness structure. So we can
Yeah.
just increase the width
Bit.
of the M2 region in that region. So we can, by
Okay.
increasing it, we have to take care of the DRC as well.
Okay.
Without creating DRC, we can do it. Okay.
Okay.
Uh, Do you know about color GDS and uncolored GDS?
Color? D-red, sir.
Color GDS.
No idea.
Okay. So color GDS and uncolored GDS is nothing. But do you know mask and unmask, about mask region? So in 14 nanometer, do you know about coloring? Like,
Metal colorings.
yeah.
Yes.
So on what metals do you like, for what metals, on what layers or what wires do you see that for?
Metal one is tail color. I couldn't remember the exact colors, but I can give you
No, not about colors. So on what layers you see? Just on what layer? From one M to
colored layers. So,
on like on what layer?
sorry, I didn't get the question.
Do you know what? Okay. So the color GDS and uncolored GDS is like, for example, I've opened for the 3 nanometer. In 3 nanometer, color GDS is nothing but masking of the layers.
Yeah.
For example, M0 colored, M0 has colored mask, M2 in 3 nanometer,
Okay.
M2, M5. So these are the colored layers. So for different active nodes, the masking has to be changed. I'm asking for 14 nanometer, you open for 14 nanometer, do you observe any like color GDS in that region? Like for on what layer, on what bias?
Or I haven't observed any.
Okay.
I think your voice is
Mhm.
not coming properly. I think your voice is not coming.
Sorry, I didn't.
Yeah, now it is fine.
I didn't observe any of those.
Okay. For example, you get a error on wire error.
Okay.
on wire 3,
Okay.
and you are changing from wire depth from metal 2-stack to single stack wire.
Okay.
So will it affect the EMI?
Yes, it will definitely affect because the resistance will be more in static wires rather than normal metal wires. So if the resistance is less, then it will definitely affect prone to the EMIs in a normal
Okay, okay,
rather than static wire.
okay. Tell me about ERC.
ERC. Electrical rule checking, it's nothing but checking for opens and shorts nowadays.
Mhm.
Sorry, I couldn't
Okay,
remember.
take the time. Okay,
Sorry.
okay. So ERC is for always is for checking for both signals and power everything. ERC is for electrical rule to check only for the correctness of power and ground.
Okay.
So only for power and ground will check like, for example, annual opens, annual shorts, everything in the design. So for example, any two cells got overlapped or any orientation issues in the design, you can find the others.
Okay.
So for checking the correctness of power and ground, the ERC will be used.
Okay.
Uh, okay. This cells SSB.
Sorry, your voice is breaking.
Do you know about SSB cells?
SSD, solid state drives.
SSB, synchronous numbers. Do you know about those cells?
Sorry.
Okay, fine. Yeah, okay, fine, Likit. If you have any doubts or any questions, you can ask.
Uh, how was my interview? That's the question.
It was good. Okay, yeah, you got most of the topics. Uh, so it's fine. It was good, but you have to learn deep into the topics.
Yeah.
So that's the thing. For example, you know about antenna,
Yeah.
but you should learn the deep, like you should learn deep into the topic. Apart from that, yeah, good in the interview.
Yeah.
Yeah. So only 14 nanometer you work or any other?
14 nanometer and 28 nanometer for design.
Okay,
Using
fine. Yeah.
PLL.
Yeah, okay, yeah, good to look at your performance.
Yeah.
Okay, Rajit, yeah, shall I leave the call?